Hello and welcome to another lecture on circuit theory. Today we will be defining the electrical quantities such as voltages and currents in terms of the fundamental physical quantities, which all of you might know from a basic course on physics. So quantities such as force. So what is force? So force, as you all know from Newton's second law, is F is equal to ma, where force is a vector quantity as well as acceleration, and it is mass times acceleration. So a force of 1 Newton is defined as a force which is required to move a mass of 1 kilogram with an acceleration of 1 meter per second square. Next, what is energy? So energy can be defined, or kinetic energy can be defined as the energy required to move a 1 kilogram mass with a velocity of 1 meter per second. Then what would be the kinetic energy? It would be, according to half mv square, it would be half a joule. The next quantity we will consider is power. Power is defined as the rate of doing work. So energy is denoted with W, force with F, and power is rate of doing work. So power is dW by dt. So the unit of force is Newton. Energy is defined in joules. So the energy required to move a 1 kilogram mass with a velocity of 1 meter per second is half a joule, according to this formula. And power is rate of doing work, and it is given in watts. So the next fundamental quantity is that of charge. And in electrical engineering, we are concerned with electrical charges or electrons. So electrons, an electron is defined as 1.602 into 10 raised to the power minus 19 coulombs. And from here we can define 1 coulomb as 6.24 into 10 raised to the power 18 electronic charges. Now current, as we know, is defined as the rate of change of charges, so dq by dt. And from here we can see that the unit would be coulombs per second, since charge is given in, and it is named after the great electrical engineer Ampere. The unit of current is ampere. But there is also another interpretation for defining a charge. So charge can be defined as in terms of force. So linking charge to force, you know that force is equal to Q times E. So 1 Newton is defined as the force on a unit positive charge in an electric field of 1 volt per meter, so where the unit charge is given in coulombs and this is in Newton. So this is another way of defining charge. So let's look at this expression once again. F is equal to QE. So imagine that the electric field is in this direction. So this is E, and we have a positive charge here and a negative charge here. So the force experienced by the positive charge would be in the direction of the electric field, while the force experienced by the negative charge would be against the direction of the electric field. And this would become quite important when we would look into semiconductors like diodes and transistors, because there we have positive charge carriers as well as negative charge carriers. So in a case where we have both of them, the current will be the rate of change of positive charges plus the rate of change of the negative charges. This would give us the total current. Now moving on to the next quantity. What is an electric potential? So electric potential, denoted by phi, is also a vector quantity. It is defined as the force required to bring a unit positive charge. Let's say I have a unit positive charge which is at infinity. So the force required to bring this charge from infinity to a certain point is called the electric potential phi. And voltage is nothing but the potential difference between 2 points. So let's say if this charge, if the potential here is phi1 and the potential at this point is phi2, the voltage would be nothing but the potential difference between these 2 points, phi2 minus phi1. So in electrical engineering, we always fixed one of the potentials. So phi2 is normally chosen as reference, which is connected to the earth. So this is a grounding symbol. But we should always remember that voltage is always defined with respect to a point. So if I say that this is a 12 volts battery, it always means that the potential here is 12 volts with respect to ground, where the other terminal is at zero potential. Now, what is the relation between potential and electric field? So for instance, if I have 2 points, one of them is at potential phi1 and the other one is at potential phi2, and I know that the electric field is increasing in this direction. So the electric field, which is a vector, is increasing in this direction. So it means that the potential at this point would be higher than the potential at this point, because electric lines of force always emanate from positive towards negative charges. So let's say if this here is a negative charge and here it is a positive charge, so the potential at this point would be higher, let's say 10 volt, and here let's say 2 volts. So electric lines of force, so these are the electric lines of force will emanate from this positive charge and go towards the negative charge, and the electric field would be from positive to negative. So we see that the electric field is in a negative direction with respect to the higher potential. So it's given by d phi by dx. The potential here is higher, but the E field is in the opposite direction. So this is according to the Faraday's law. This is also important to remember. Another thing we should keep in mind that the charges may not always be stationary. So this Q1, if it is stationary and I bring another charge close to it, Q2, then the force between them, there will be some lines of force, as we see, can be given by QE, for the electric field. But this charge can also be moving. So if this charge is moving, then we come across the term which is magnetic flux density B. This can also be defined in terms of the fundamental quantities. So the force experienced by a unit positive charge when moving with a velocity of u is given by this relation. So 1 Newton is the force experienced by a unit positive charge when moving with a velocity of 1 meter per second in a magnetic field of 1 Tesla. So this is named after the great Serbian scientist, also known as the founder of electrical engineering, Tesla. But in this course on circuit theory, we won't deal that much with magnetic flux density, but we should always keep this in mind. We will take a deeper look into this when I'll start the course on electricity and magnetism. The next thing I want to consider is power. How to define power in terms of the fundamental quantities. So imagine I have a charge here, Q1. Let's call it dq. So it's an elementary charge, and I want to move it over a potential difference of V from phi1 to phi2. Then the work that would be required, dW, would be equal to this potential difference V times the elementary charge dq. Now we have already seen that power is nothing but rate of doing work, so dW by dt. So I can write this as dW by dq into dq by dt, and dW by dq is nothing but the voltage from this relation. So this, let's say, is 1. So power would be equal to V times dq by dt is nothing but the current. So the power in an electrical circuit is nothing but the product of the voltage and the current. And what if I want to find the total energy in the circuit? So from here, since power is the rate of change of work, I can find the energy as the integral from power from minus infinity to t dt. So here in this lecture we have defined the electrical quantities such as current, voltage, here we define voltage, and power in terms of the fundamental quantities such as force, energy, and charge. So this was all for today's lecture. In the next lecture we will continue further with our course on circuit theory. Thank you very much.